Ishrae helps formalize industry codes and standards. Ishrae promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, Ishrae Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, Ishrae Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. Ishrae organizes exhibitions, conferences, panel discussions, and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, ACREX India, to showcase the cutting-edge technology, innovation, and provide a platform for closer interactions amongst the decision makers in the industry. The ACREX exhibition is now growing from HVAC and AROUL show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry, all at one location. Our chapters organize several other popular events like AgriConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A-Quest, a prestigious quiz competition organized by Ishrae to catalyze the transformation of the budding engineering professionals. Ishrae provides a platform to potential employers to select student members for careers in HVAC and our industry at the Ishrae Job Junction. Young minds are made aware of the need for saving power, clean air and sustainability. The K-12 initiative of Ishrae focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVACR and building services industry with just a few clicks. Ishrae cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection and energy efficiency and conservation to enter and explore the universe of the Indian HVACR industry. Log on to ishrae.in that unfolds a panorama of information. Let us engineer a sustainable future together through Ishrae.
Admissions open. SRM Ishrae Engineering College.
Good evening to everyone. We will start the session. Okay, so I will start my presentation. Okay, first I will start presenting my screen. Good evening to everyone. Welcome to the uh, 2 weeks online workshop on energy simulation and CFD analysis in building. Today is day 4. So we are going to discuss about cooling and heating load calculation and energy simulation. So previously I was thinking of teaching you the load calculation, but most of you might have attended a lot of seminars and lectures on load calculation. So I want to link this load calculation with the energy simulation. So that is what I am going to do today. Okay. So I'll be discussing about load calculation, salient features of load calculation. So then I'll be discussing about energy simulation and how both are related. So that is what we are going to discuss today. Okay. Okay. So what are all the components of load calculation? Okay. So already we may be knowing. So if you are going for a cooling load calculation, so we have two types of calculations. One is cooling load calculation. The other one will be a heating load calculation. Cooling load calculation, we do it in a hot places. Okay. So you take a case like this. Okay. So what are all the components of the cooling load? So the components of the cooling load are the external, okay, solar energy entering inside. The solar energy will be entering inside through the walls, through roof, through the windows. So windows means there are two possibilities are there. One is a glass, okay. In the window, you can have, okay, a wooden door for window, as well as sometimes the glass will be transparent. Okay, so if the glass is transparent, okay, so it includes the radiative component. Okay, but if this glass is not transparent, okay, so if it is a tinted glass, if it is a tinted glass, or if it is pasted with the films, okay, so there will be more absorption components. So in that case, heat transfer is possible. Okay, so heat transfer only is possible. So windows will be transparent if transmissivity is higher. Okay, if absorptivity and reflectivity is higher, there is more possibility of conduction or conduction heat transfer. Okay, and about partitions. Okay, so heat transfer can take place between a conditioned room and unconditioned partition. Okay, or room existing outside with a partition separating. Okay, so from a heat can be transferred from a unconditioned place to a conditioned room. Okay, so the separating link, it is called as partition. So there can be heat transfer from the ceiling and the floor also. Okay, so these are all the components of external solar energy which can enter inside the building. Okay, and we will be having internal components also. So in the internal components, mostly it will be constant. For example, light means the wattage of light will be mostly constant. Similarly, fan, the wattage of the fan will be constant. Okay, and the heat released by the people. Okay, so it depends on the activity. If the activity level is less, like if you are having in the offices and other buildings, So that also it will be remaining constant. Okay, but the people will be releasing both sensible and latent heat. Okay, so we will discuss subsequently. And appliances. Okay, so appliances also mostly it will be releasing a constant amount of heat, except that cooking appliances if it is in the conditioned room. Okay, so that may be varying. Okay, and the equipments, you may be having some equipments like computers, heaters, oven. So all these things you can have it inside the room. Okay, so that may contribute for the load. Okay, and the next component of the load is infiltration. Okay, so infiltration, it is unwanted entry of atmospheric air, hot air, into the conditioned space. So when it is infiltrating, okay, so it will bring in the load, okay, in two forms. One is sensible form, other one is latent form. Because if you are air conditioning, your indoor temperature will be around 24-25 degrees centigrade. Your outdoor temperature will be around depends on the condition. Okay, for Chennai it may go up to 40 degrees centigrade also. Okay, so that means the air from outside, if it is infiltrating into directly into the conditioned space, so then we will be having two components. One is the sensible component, the other one will be the latent component. Okay, and also I'll be having system heat gains. System heat gains means when you are having an air conditioning system, so you will be having a duct, reheater, fan, pumps, all these components will be there. So the heat released by these components are called as the system heat gain. Okay, so all these components can contribute for uh, heat gain into the building. Okay, so that is what we are going to discuss today. Okay, that is what we have discussed already, but we are today we are going to discuss. Okay, a little you are going to go one step further. Okay, so and we have seen what is that we have seen yesterday. Okay, so we have seen that if you have a conditioned space, okay, so if you are having a conditioned space like this, okay, so the heat will be entering from outside. Okay, so the heat will be entering, so the solar radiation will be entering from outside. Okay, so it may directly enter through the glass. Okay, transparent component. So you may having opaque components also. Opaque components means it may enter through the wall. Okay, so conductive components. So infiltration will be there. Just now we have seen internal heat generation will be there. So all these things will be trying to heat the building. So that also I told you already. And the air conditioning system what we are having, okay, so that will be trying to remove the heat from the system. Okay, so this is the cooling coil, a refrigeration system. The cooling coil is located here. So this will try to remove the heat. Okay, so remove the heat. So the return air will be coming hot. So when it is entering here, so it will be losing its heat to the cooling coil. Okay, and it will be going as cold air inside. Okay, cold and dry air as inside. So this is what is happening. So yesterday we have discussed these components in the psychrometric chart. Okay, so in the psychrometric chart we have all these components. For example, so this is the room condition or return air condition. Okay, and this one what we are having here, so it is the outdoor air condition. Okay, so you may be knowing, for example, if you am having Chennai, so the outdoor air condition, it will be at the peak, it may be around 37 degrees to 40 degrees centigrade. Okay, so that is the outdoor condition. Okay, so this you will be having the room design condition. So the room design condition, so will be mostly maintaining near 24 to 25% and 50% RHO. So that is what we will be maintaining. So yesterday we have seen that we will be mixing the outdoor air and the return air. Okay, so the mixing psychrometry also we have discussed yesterday. So so this is the thing. I'm getting the return air from the room. I am mixing it in the outdoor air, fresh air. So the resultant condition is water. So mixing air condition. Okay, so that is mixing air condition. So this is mixing condition. So from there, where it goes, it will be going to the cooling coil. Okay, so here it goes to the cooling coil. So as it goes to the cooling coil, what is happening? So the air is getting cooled and dehumidified. Cooling and dehumidification will be taking place. So this process from M to D, so it is a cooling and dehumidification process. And you will find that as the air is moving, okay, so if it is 100% effective, okay, so then the air will be leaving at the point D. But you know, any heat exchanger, so it will be having an effectiveness. So because of that, what happens? The air will not be leaving at the condition D. Some amount of air will be bypassed. So, or I can say it is an inefficient portion. Okay, inefficient portion of things. So that will be bypassing. So the resultant air will be moving only at air will be at the condition yes. So that is called supply condition. Okay, so this is the supply condition into the room. Okay, so this is the supply condition into the room. Okay, so this is the return air condition. So S to R, okay, S to R, what is happening? So S to R, the air which you have supplied, it is at cold and dehumidified condition. So once it is entering the room, what is happening? So the heat is added to the air, and air is getting humidified because of the load. So this is very important. So I have told already, but I'm telling, because this is very important. We should understand. So when the air is entering the room, so it is getting heating and humidified. Okay. When the cooling coil, only cooling and dehumidification will be taking place. That is M into S. So that is what it will be happening. Okay. And so yesterday we have discussed how to calculate the total tonnage. Okay. So the total tonnage, I have to take SR component, RS component, and MR component also. So because of mixing, outer air will be entering. Okay. So the resultant of these two is MS. Okay. 1 minus by 4 into MS. Okay. And the bypass portion also, we have to add energy for that. That we should know. Okay. So we have to give energy to the compressor for cooling. Okay. So because of that, my this component also I have to add. So totally I'll be having all these components. Okay. So in the heat load calculation, I'll be having room SR, that is room sensible heat and room latent heat. So the horizontal component of this line is that is the sensible portion. Yesterday we have seen this is sensible. Horizontal component of SR is sensible. The vertical component of this is latent load. Okay. Similarly, the horizontal component of this, okay, so that is sensible, and the vertical component is latent. Similarly, here also horizontal component is sensible and vertical component is latent. So that is what these components are appearing in our heat load calculation term. Okay. And in effect, okay, so in effect, for a fact, we have a factor called as effective sensible heat factor. So what is the effective sensible heat factor? What is its purpose? So during the load calculation, so we will be calculating effective sensible heat factor. That is effective sensible heat divided by effective total heat. So when I have the effective sensible heat divided by effective total heat, so I have effective sensible heat factor. So what is the use of that? Okay. So you can draw the line, effective sensible heat factor line with that slope. Okay. So through the R, so from there it will be going and touching the saturation line. So that is ADP line. Okay. So as per room condition, okay, so the ADP should be somewhere here, but I'm bringing down the ADP. So how to find that ADP? By finding the effective sensible heat factor line only. And what is the use of this effective sensible heat factor line? So the use of effective sensible heat factor line is to select the AHU. Okay, so AHU volume flow rate. So you'll be having the AHU. So what is the volume flow rate of AHU? What is the flow rate of AHU? Okay, what is the capacity of AHU? So that is decided by using the definition of effective sensible heat. Okay, so effective sensible heat, we have seen that it is equal to, okay, effective sensible heat, it is equal to MCP del T. Okay, so that we have seen yesterday. So using that, we are going to find out what is the volume flow rate of air. Okay. So we will go by order. First, we will find out what are all the room heats. So room heats are room sensible heat and room latent heat. Okay. So whatever the heat load, what I'm having inside the room, okay, inside the conditioned room, so that is room sensible heat. So the loads which are added inside the conditioned room, that is room latent heat. Okay. And the load pattern. Okay, the load pattern of room will be based on a room sensible heat factor. Okay, the ratio of latent heat to sensible heat to room total heat. So that will tell you how much will be the latent heat and how much will be the sensible heat. So that will be useful for us to decide the cooling coil. Okay, so if you are having a high latent application, so you will be going for a very low ADP with more number of rows of coil. Okay. So that for that it will be useful. Okay, and from here we are going to, what are the other components we will be having, other components of the load. So room total load is there, whatever the load which is there inside the room, so the sensible and latent, so that is called the room total heat. Okay, and we are taking outside air. Why we are taking outside air? So we are taking outside air because we are having occupants inside the room. So if you are taking occupants inside the room, so each one of them, they have to breathe, they require oxygen. So there is a minimum standard by which we have to give oxygen to them. So suppose one person is there, so I have to give, okay, so for example 10 cfm per person. So that means if 4 persons are there, I have to give 40 cfm. Okay, so like that I have to multiply. So it will the number of or the quantity of air which I am taking inside, so that is going to be depend on the number of occupants. For example, if it is going to be like a theater, okay, so there you may be knowing that the number of occupants will be more. So that means the ventilation, what amount of outdoor air which you have to take in a theater, it should be definitely high. So when the outdoor air it is coming, okay, from outside into the conditioned space, what will happen? It will bring outdoor air sensible heat. So what is the meaning of that? So it you have a indoor room dry bulb temperature, you have outdoor air dry bulb temperature. The difference between that, okay, so that will be the sensible heat component, okay, or the sensible heat component. You, that is mcp delta only. So volume is there, density is there, multiply that, you'll be getting mass, specific heat, and the delta. What is that delta? It is outdoor air dry bulb temperature minus the room dry bulb temperature. So this difference, okay, this mcp delta will give the outdoor air sensible heat component. Okay, then what is the outdoor air latent component? So outdoor air latent component is that, so I am going to take the same, the quantity of air, it is going to be same. It is dictated by the ventilation standards, or it is dictated by the number of occupants. Okay, so the same quantity of air I am going to take here. Now the out in a summer air conditioning, the outdoor is going to have higher humidity and indoor is going to have low humidity. Okay, so when you know, so you want to maintain at 50% RH. So what is the corresponding humidity, specific humidity? So that will be the room humidity. That is the room humidity. The outdoor air humidity, it is going to be from outside. So it is definitely, it is going to be higher, because yesterday I shown you in the psychrometric chart. So at the indoor condition, it will be almost down in the vertical axis, that is specific humidity axis. But the outdoor condition, it will be very much higher. Okay, for example, in Chennai and all, it will be very much higher. So that means a large latent load will be there. So if the specific humidity difference is there, okay, so you have to condense. Okay, so you have to condense this much amount of water. Because of this specific humidity, if I multiply by mass flow rate of air, I will be getting the water quantity, okay, so which is entering inside. So how to remove the moisture from the air? So that means I have to condense this air. So this condensation, it will take place in the cooling coil, because the cooling coil temperature, it will be naturally, okay, less than the dew point temperature. So because of that, the moisture will be settling on the surface of the cooling coil, and because of that, the moisture will be removed. But for that, we have to take all these things in load calculation. Okay, so how we are doing? So we are taking what in the conditioned space, what is the specific humidity? In the outdoor, what is the specific humidity? So that difference we are taking, and that specific humidity, if I multiply with the mass flow rate of air, okay, so I'll be getting the mass of water, okay, mass of water which is entering into the room, mass of water which is entering into the room, okay, per minute or per second. So then what I have to do? If I want the heat, this water, the quantity of water, I have to multiply with the latent heat. Okay, so we call it as H of G. So that means this mass flow rate, the mass flow rate of water multiplied by the H of G. So that is the heat component that is entering. So that means your cooling coil should have the capacity to condense this much quantity of moisture. Then only you can create the condition inside the conditioned space. Okay, so that is what I call it as the outdoor air latent heat. Okay, so this component, this represents the specific difference in specific humidity, and this is mass, volume into density is mass, and 50, this component, it represents the latent heat. Okay, so this is outdoor air latent heat. Okay, so when I club both together, so I'll be getting outdoor air total heat. Okay, so that both will be contributing for rising the tonnage in the room, or rising the heat gain into the room. Okay, so the next component is, what is the total load? What is the total load? So the total is load, total sensible load is total sensible heat, okay, So that is room sensible heat plus outdoor air sensible heat plus the system gains. Sensible system heat gains. Okay, air conditioning system gains means it is sensible system heat gains. Okay, okay. So which is including all these things: supply air, return air, duct air leakage, sensible. All these sensible components will come here. Okay. And what is the total latent heat? So the total latent heat is room latent heat plus outdoor air latent heat. Room latent means it is possible that the moisture can be generated into the room, because if you think of theaters, so many people will be sitting in a theater, so that means a lot of moisture generation will be there inside the theater. So because of that, what will happen? Latent heat will be added. Okay, so that is room latent heat. Okay, and outdoor air latent heat is for these people who are sitting inside the theater. Okay, you are taking air from outside for oxygen requirement. As per ventilation standard, you are taking air from outside, so that is outdoor air latent heat. Okay, so then you may be because of supply air duct leakage, there may be latent losses, so that also I had to add it. So this is system latent heat. Okay, so that means it's very simple only. You are just summing all the load. Okay, so when you are going into the heat load calculation form, so there will be different components. Okay, so you will be having a one minus bypass one place, and another place the same thing with the bypass you will be getting. So we are going to see that. Okay, but if you just want only tonnage alone, what is tonnage? First, what is tonnage? So it is the rate of heat gain in the building. So that is the tonnage. Okay, so if you just want the tonnage, just add the total sensible heat and the total latent heat. So I will be getting the grand total heat. Okay, so that is it. Okay, so that is it. So why we are going for the effective sensible heat or effective sensible heat factor calculation? So that is not for energy requirement. That is not for energy simulation. So that is for designing. Okay, that is for designing. So for designing, you require a fan. Okay, so we require a fan for the air handling unit. So that fan should be having the sufficient capacity. Yesterday we have seen, if it is near ADP, a lesser volume is sufficient. If it is nearer to the room condition, so that means a large quantity of air is required. So for the catering that need, okay, so we have to calculate what will be the dehumidified CFM. Okay, so dehumidified CFM. Okay, so for calculating dehumidified CFM only, this effective room sensible heat, effective room latent heat, and effective room total heat comes into picture. So we are calculating effective room sensible heat factor, and using that, and as well as choosing the bypass factor, we can calculate what is the bypass factor and ADP. Okay, choosing the bypass factor, we have to calculate the effective sensible heat factor. We have to select the ADP, and we should be selecting a coil. So by that we can fix the bypass factor. From that we can calculate what will be the dehumidified volume flow rate. Okay, supply air volume flow rate. Okay, so how to calculate the effective room sensible heat? Okay, so here again, yesterday we have studied. Okay, so yesterday we have studied. This is the effective sensible heat factor. Okay, so this is the effective sensible heat factor line. So the horizontal component of this, so it is effective room sensible heat. The vertical component of this, it is the effective room latent heat. Okay, so that means effective room sensible heat, I have a room sensible heat and the bypass factor into outdoor air sensible heat. So that is the component what we are having. So just now we have seen that. So that component is the bypass factor into outdoor air sensible heat component is there, and the air system heat gain multiplied by bypass factor. That is very, very important. Okay, so that means, so here we are taking the room sensible component, and as well as we are taking this component also, bypass factor component also. Okay, bypass factor component also. So we are taking it for the outdoor air sensible heat as well as the system gain. Okay, as well as for the system gain. So that is what we have to do. Similarly, I have to do it for the latent heat also. Okay, so because that is vertical component of this line, no? This vertical component of this line. So first we have to understand. See, if you consider this SR as a vector and DE as a vector, dr should be a resultant vector. Okay, so dr should be the resultant vector. So that means what? If you calculate dr, it will include both SR as well as ds. Okay, so that is what we are doing now. So that means the component ds we are calculating So that will be with the bypass factor, and the component SR will not be with the bypass factor. Okay, so that is what we are having here. Okay, so that I think now it should be clear for you. So we are calculating effective room sensible heat. So that is room sensible heat bypass factor into outdoor air sensible heat, then air conditioning system gain, that is sensible component into bypass factor. Similarly, we have effective room latent heat. So I have room latent heat bypass factor into outdoor air latent heat and air conditioning system gain with the multiplied by bypass factor. Okay, so I calculate the effective room total heat. Okay, then what is required for me is to find out what is the effective room sensible heat factor, because if I know the slope only, then only we can go and hit the saturation line and find what is the ADP, and you can substitute that ADP. Okay, and so to find what is the dehumidified CFM. So what we are doing here, we are just taking the definition of effective room sensible heat factor. Okay, so this is the definition of effective room sensible heat factor. So this is one form. Okay, so if you try to expand it, okay, if you try to simplify this, so you will be getting this. So what effective room sensible heat factor is dehumidified supply or CFM multiplied by density multiplied by specific heat. Okay, into room dry bulb minus ADP of coil, ADP temperature of the coil. Okay, so that is the definition. So if I want dehumidified, bring everything to the other side, so I get to what is dehumidified. So that is how we decide the volume flow rate of the AHU for a particular room where we are doing the load calculation. Okay, so now so we are ready. Okay, so we have developed a strong psychrometry for which will be paving way for load estimate. Okay, so now we are going for load estimate. Okay, so now again I will stress now. What is cooling load estimate? It is the heat gain, instantaneous heat gain. Okay, instantaneous heat gain into the room. Okay, why I'm telling that? I'm just going to link the heat load estimate or cooling load estimate with the energy simulation or energy calculation. Okay, so I that is why. Okay, so I'm going for this discussion. Okay, you will find that whatever the data which is required for the energy simulation, the same data it will be required for load calculation also. Okay, so I will tell you why in the end. I will tell you why, what is the reason. Okay, so first we will be going through the building characteristics. Okay, so that means the building construction materials. So material property is very, very important. Even in we use it in load calculation, as well as we have libraries of construction material in your building simulation software. Okay, and we are going to know the physical dimension of the space. So the load is going to vary with the physical dimension of the space. For example, column height, ceiling height, column beams. Okay, so all these things. Okay, so it is going to change. Okay, so it is going to affect the energy calculation or load calculation. Okay, so even the position of windows, stairways, and escalators, all these things, it is going to affect not only the load calculation, it is going to affect the energy calculation also, energy simulation also. Okay, so the next is configuration of the building. Okay, so we discuss about orientation of the building. Okay, so because we have in the first class we have discussed about the sun path diagram. Orientation is very important. Okay, so you may calculate the load, or you may try to reduce the load also. Okay, you may try to reduce the heat entering into the building by checking the orientation. Okay, so that means this component we are having in the heat load as well as even in the energy calculation also. Similarly, the shape of the building. Okay, so you can fix it using energy simulation software. Similarly, the shape of the building affects the load calculation. So as an architect, as a building engineer, okay, so always we should think to reduce the heat entry into the building. Okay, so that is the best design. Okay, so that means configuration, shape, shading of from adjacent buildings. So all these things are important components. First we have to understand that. So next is when we are what are all the two important parameters by which the load, the cooling load is dependent on. Or in the other side, energy simulation, what is the energy consumption, what are all the two important parameters by which the energy consumption is dependent on. So now that we have studied different location, different places, okay, so now we should be in a position to know, okay, so what are all the important parameters. Okay, so the first is weather data. Okay, so outdoor weather data. So it can be dry bulb temperature, it can be humidity, it can be relative humidity or specific humidity. In some form, you should know the humidity, latitude and longitude, because that is going to decide the location. So that we have seen in the first class. Elevation. So I think this component I have not discussed. So elevation is also important. So there should be a question. If I tell something about the latitude and longitude, so you should ask one question. See, Otakamand, you may be knowing Ooty, okay, it is our Munnar, okay, or Kodaikanal, okay. So all these things, it is there in the 10-degree latitude only, but still it is a cold, okay. But if you are if you consider some other place in the same latitude, it is hot. So what is the reason? The reason is elevation, okay. So as we go up, as the elevation is going up, because if you are climbing a mountain, elevation will be increasing, height will be increasing, altitude will be increasing. So what is the meaning? So if you I'm climbing up the hill, so you know that the pressure will be lesser, okay, density of air will be lesser, so temperature also will be lesser, okay. So that means so here the temperature reduction, it is not because of solar movement. Here the temperature reduction, it is because of the reduction in the density, reduction in the pressure, reduction in the temperature, okay. Whenever you are moving up a mountain, okay, so definitely the temperature will be dropping. So that is very common in the Western Ghats, you may be knowing that, okay. So elevation is also important, okay. So it's not only latitude and longitude, elevation is also important. That will decide, okay, the temperature, outdoor temperature and humidity, okay. So next, period and time for calculation, okay. So always we calculate at the peak period, okay, peak day, peak time, okay, peak heat value. So that is how we calculate. So and also the energy simulation or the load calculation, it is dependent on the indoor design condition. So indoor design condition, indoor dry bulb temperature, indoor relative humidity, and ventilation requirement. It's very obvious. You think that suppose we have air conditioners in our room. If I am maintaining my room at 25 degrees centigrade, okay. So what is the meaning of that? So that is normal thing. So it is also possible that in some places, okay, so they may be maintaining the room at a very low temperature, okay. So some may be maintaining at 18 degrees centigrade. Out of these two, which will be consuming more energy? It is very obvious that those who are maintaining the room at 18 degrees centigrade, they have to they will be consuming more energy, because the temperature delta is higher, okay. Delta, it is calculated by UA delta. The delta is higher for the second case. So that means if the room temperature is going lower and lower, similarly if the room humidity is going lower and lower, so that means the gradient, okay, so the gradient is increasing. So because of that, the energy required for cooling, that also it will be increasing. So energy requiring for cooling means it will contribute for cooling design. We are going for energy simulation software. So that means energy consumption in the room, it will be increasing. Energy consumption in the room, it will be increasing. So that is very obvious, okay. So for example, if you are maintaining at 25 degrees and at 50% RH, so if it is consuming one electrical unit, okay. So if you are going for 18 degrees and 40% RH, and still lower than that, okay. So it may be consuming 3 units. So that is what. So from the energy point of view, and for initial design point of view also, so this is very important, okay. So indoor design conditions, that is dry bulb temperature, relative humidity, these are all two important things. Similarly, ventilation requirements. So for example, if you take a theater, the theater without occupants, okay, without occupants, that means if there are no 300 people in a theater, so the load or the tonnage what you are going to get, it is going to be smaller only. But if people are entering inside, so then the load is going to increase, because this is because the people sitting inside, they are giving a sensible load, latent load, that is different. But for catering these people, you are going to take air from outside. Ventilation, as per ventilation standard, you are going to take air from outside. You are going to pump it inside. So that means there also your requirement, okay. So the requirement of energy, it is going to increase. So when air is coming from outside, okay, so it is going to bring the load also. So I think that is obvious. So similarly in the control limits also, where you are putting your setting, Okay, so that is like fixing the dry bulb temperature only. Okay, lower settings, higher the energy consumption. Okay, in summer air condition. So then internal loads also it will be deciding lighting, occupancy, and equipments. I think we are discussing again and again, and system gains. Okay, so duct heat loss may be there if you are not insulating. If the quality of ducts is not proper, leakage is there. Fan energy. Okay, so fan may add energy to the your conditioned air. So return air, okay, heat gain may be there in the return air. So outside air, okay. So and what is the type of system we are using? So in all this place, so gain may be there. Okay, heat gain means the rate of heat entry into the building is increasing. What is the meaning of higher tonnage, higher? So the meaning is the rate of heat entry into the building is increasing. Okay. Okay, now we are going to the load calculation. So I'm not going to discuss more about the load calculations. I'm going to discuss about the salient points alone. Okay, so what are all important points in this load calculation? That is what I'm going to discuss. Okay. So indoor design condition. Okay, so first indoor design condition. So it will be different for different places. So for example, industrial. So the indoor conditions may be depending on the product. Okay, so if you are going for a shop, okay, so that is commercial complex. So the indoor condition it is going to be based on the requirement. For example, bakery. So that is going to be different. Okay, for a textile, it is going to be different. So indoor condition, so it will be different for different thing. Okay, I'm not purposely I have not shown this thing properly because you can refer this from the data book. Okay, you can refer this from the data book. So just like it is available in the data book. So that is the message I want to convey. So indoor conditions, it will be different for different place. Okay. Similarly, the indoor conditions will be different for summer and winter. That is what we are seeing. Similarly, with the humidification, without humidification. So indoor conditions are different. High latent load application. So it will be different. Factory settings, it will be different. So indoor conditions, it is there in the data book. You can go and see what is the prescribed recommended inside conditions. Okay. So I'm leaving it to you. So you can go and see that. So our objective is not that. Okay. So the next is outdoor design condition. So outdoor design condition means for each city. Okay. So outdoor at peak. Yeah, I am underlining at peak day, at peak timing. Okay. So what is the condition? So that is what is given here. Okay. So for example, if Chennai means, so there will be, so you see for 13-degree latitude. So May, first week of May. Okay. Or April end or May. So it will be higher. So that means you have to find the time wherein the direct radiation from the sun falls exactly at that latitude. Okay. So for that you will be having a particular time. So for that corresponding time, what is the dry bulb temperature? What is the wet bulb temperature? What is the RH? That is very important. So that means outdoor. So like that for each place it is given in the data book. Okay. For each place it is given in the data book. Again, I'm just showing the sample. Please refer to the data book. You can go and refer to the data book. Okay. So there you can see for each state or each city, they will give what is the outdoor design data. Outdoor design. So they are given 3 data. Why? Because you have to do 3 calculations. So you can do summer calculation. You can do monsoon calculation also. Because sometime in monsoon, the latent load may be very much higher. So that means the tonnage required in the monsoon, it will be very much higher compared to summer. So that means you can, for avoiding the ambiguity, you can do a calculation in summer, you can do in monsoon, even in winter also you can do it if you are going for heating. Okay, if you are going for a combined system, combined heating and cooling system like Delhi. Okay, so there you can have both heating and cooling system. So there you have to take winter conditions also. So this is very well available in the data book. You can always refer. Just I am showing for Chennai. For all the other things also it is available. Okay, in standard data book it is available. Okay. Okay. So now these are the 2 important things. So the next is what is the amount of radiation received? Okay. So what is the amount of radiation received? So how it is going to affect the building? So the amount of radiation received definitely it is going to affect the building. So we have the glass mostly if you will be having glass, okay, and other applications. So in the glass, okay, so directly the radiation will be entering into the building if the transmissivity is higher. Okay, so that means what is the maximum amount of radiation that will be received? Okay, instantaneously. So that we should know. So the maximum amount of radiation alone, it is given for various latitudes. So I think whatever we have studied in the first session, it will be useful for identifying. Okay, so here you can see, if you can take when I'm at 0 degrees north latitude, I think both should be same. 0 degree north latitude and 0 degree south latitude, both will be same only. Okay, so what is the time at which you will be getting a maximum radiation? Okay, very simple. As per our knowledge from the first session, equinox, equator, 0 degrees means it is equator. So at the equinox, you will be getting maximum radiation. What is the equinox? Two equinox are there. One is a March equinox and a September equinox. You can come here and you can see the value is 250. For horizontal, it is 250. Okay, so that means that is where we will be having maximum radiation. So this radiation is in watt per meter square. Okay, it is in watt per meter square. Okay, meter square area. So next, if I am going to 10 degrees, okay, 10 degree. Okay, so for example, Chennai is in a 10 degree north latitude. So from this side it is 10 degree north latitude. So from this side it is a 10 degree south latitude. Okay, okay, for 10 degree south latitude, what is the location at which I'll be having a maximum radiation? Okay, so what is the time? Okay, so it is August and April. Okay, August and April, I'll be having maximum radiation in the northern hemisphere. You can see for northern hemisphere it is August and April. So when I am moving to southern hemisphere, it will be October and February. This we know. Okay, so whenever whatever applicable in the northern hemisphere, exactly opposite thing will be happening in the southern hemisphere. Okay, so here maximum radiation it is in August and April, and in the southern hemisphere it is in October and February. Okay, next we will proceed to 20. Now we are nearing the 20 degrees north latitude and 20 degrees south latitude. So that means we are nearing the Tropic of Cancer and Tropic of Capricorn. Okay, so near that tropic, if I am nearing the Tropic of Cancer and Tropic of Capricorn, solstice should come to your mind. So that means near solstice only I should get, but it is not exactly solstice. Solstice means it is 23.5. June solstice 23.5, but we are at 20 degree north. Okay, so 20 degree north means so I'll be having maximum value at July and May in the northern hemisphere, and on the southern hemisphere it should be in near the December solstice. Okay, so November and Jan. Okay, November and Jan. And when I'm going to 30 degree north latitude, so you know sun will be moving only up to 23.5. Beyond that it will not move. So that means what? So beyond this 20, it should be always June and December only. Okay, it should be always June and December only, because it is a June solstice and December solstice. So here you can see 30 degrees. What is maximum? 250. So that means December and June solstice in the northern hemisphere and December solstice in the southern hemisphere. That will be having maximum radiation. Similarly, when I'm going for 40 degree north latitude, okay, so I'll be having again 237. So December, June, and December. So you should know, after moving beyond 23.5, so only solstice will have effect. Okay, maximum radiation will be getting during solstice. Okay, so here you can see 40 degree, again it is June only, and in southern hemisphere again it is December only. 50 degrees also, again it is June, and again it is December only. So see, whatever we have studied in the first session, it is useful for us when we are going for calculating the heat load also. So this will decide. Okay, so this will decide. So what is this value? This is the maximum value of radiation. Okay, so at a particular month, at a particular location, that is particular latitude. Okay, so that means at a particular point of time, what is the value? So that is what is given. But if you want to do a calculation for one day, so then the data should not be like this. Okay, then the data should be like this. So this is given in the SI unit. Okay, so but here it is given in the, this is given in the FPS unit. So here it is given in the SI unit. Okay, so SI unit, it is we will feel comfortable. Okay, so most of us are students and professors, so we will feel comfortable with the SI units. Okay, so here you can see the solar heat gain through ordinary glass. It is given for various timing. Only daytime you will be having the thing. Okay, so radiation. So that is what is given. And at 0 degree latitude, the sun is overhead at March and September equinox. 0 degree latitude means what? It is equator and the equinox, March equinox and September equinox. So at that point of time, I will be getting the maximum radiation. Okay, so I can see. So this is June. Okay, June, Okay, in the north latitude it is June, the south latitude it is December. Okay, so let us see in March and September what is happening. So here you can see in March and September the value of radiation, you can refer to horizontal. Okay, the value of radiation it will be higher. Okay, so here it is 773 October, February. Here you can see 789, 757. So now I think we have a feel of what is happening. Okay, because we have studied about the seasons, we have a feel of what is happening here. Okay, and this is for the 0 degree latitude. Okay, so even you can see, you can refer to other things also. Okay, so other directions also, what is happening to east, west, other things also we can do it. Okay, we will move. Okay, so when we are going for 10 degree north latitude, okay, the sun will be overhead in the August and April. Okay, so that is two positions will be there when sun is moving towards north and when it is coming from the north. Okay, so two positions will be the sun will be overhead in August and April. So at that point only I will be having maximum radiation. Similarly, when I am at the 10 degree south latitude, the sun is overhead at February and October. Okay, so 10 degree north latitude. Okay, so if you can see 10 degree north latitude, so August and April. Okay, so this is August and April. So here we will be finding the values will be higher. Okay, so west, I think horizontal it is not there, below that it will be there. And similarly, when it is, I'm going to the southern hemisphere, 10 degree south latitude, the sun will be overhead at February and October. Okay, so February and October, and I think here it is there. Okay, so in the south, okay, so in the south, this will be the maximum condition. Okay, south, this is the maximum condition. Okay, so you can see, you can refer. Okay, so you can refer to the comparing to the other thing. Okay, in the south. Okay, so during February and October, okay, the sun will be overhead. Okay, so February and October, but you have to see in the February October it is not here. Okay, February October I should not see here. I'm seeing here, that is not correct. Okay, so I have to see February and October here. Okay, so that is what is correct. Okay, because this is south and this is north. Okay, so north, and you can see August and April 10 degree north latitude, so it is there here. Okay, and same condition it is there at February and October, so it is there here. So that means this table will be maximum throughout. This table will be maximum, so that's what we have to know. And mostly for design calculation we are interested in higher value, highest value. Okay, but if you are going for energy simulation, we are interested in all the values. Okay, throughout the day we are interested, throughout the year also we are interested. Okay, so that is what this data becomes important if you are going for energy simulation. But if you are interested in load calculation, only maximum values are important. Okay, so then when I'm going to the okay, so I think 10 degree, so the same thing, we will go to 20 degree. Okay, so in 20 degree the sun will be overhead at May and July, so that just now we have seen. And similarly in 20 degrees south it will be overhead at January, so it will be nearer to equinox, June equinox. Okay, so this will be nearer to December equinox. Okay, so then just now we have seen that, and now you can see when the radiation will be maximum, May and July. Okay, in the northern hemisphere, so May and July it is there here, and in the southern hemisphere it will be Jan and November. So here you can see it is Jan and November in this plot, and you can see the radiation values. Okay, so this will be maximum. You compare this with this and this confidently, you can find that this value will be higher. Okay, so this value will be higher, so this value only will be taking for calculation. Okay, so for maximum solar load we will be taking this value only. Okay, but if you want to calculate the energies, all these month values you can take it for, you can even do the year round calculation also, you can do 1 month calculation also, you can do 1 day calculation also, because for all the 12 hours they have given the values. Okay, so now you see, if you want energy simulation, you are going to utilize the full data. If you want load calculation, you are going to utilize only the maximum data. Okay, so next I am going to the 30 degree north latitude and 30 degree south latitude. Here it is obvious, it is June and December only. Okay, so here you can see June and December, this only will be maximum. So always calculation will be done for June and December only. So if you are beyond 23.5, the calculation will be very simple for you. So it is just June and December equinox only. Similarly, if I go to 40 degree north and south latitude, again June and December only. If you want, you can see. So this value will be greater here only, horizontal. Here you find it will be smaller. Okay, for each direction it is given. Don't always refer to horizontal. Horizontal means it's for roof only. Okay, but if it is east, west, north, and any direction, so it is given. Okay, so Okay, so then if I'm going 40-degree north latitude, also the same story. Okay, so same story. I'm going to have uh, June and December only. Okay, so only inside the Tropic of Cancer and Capricorn. So two positions will be there. Yeah, I have to find out from the table. Okay, but beyond 23 and half, so it is June and December solstice only. Okay, so very interesting. So next we will go for the walls. Okay, so if I'm going for the walls, so we are not relating to the temperature. Okay, so we are not. How we are calculating? So mostly radiation in watt per meter square. If it is glass, just multiply by the area, and sometimes the coefficient will be there. If it is a clear glass, the full radiation will be entering inside. Okay. If it is going to be a tinted glass with some transmissivity, with some absorptivity, some reflectivity, so that means the value it is going to be reduced. Okay, so for incorporating that, we have some we have a coefficient. Okay, so we have a coefficient for comparing. Okay, so that coefficient it will compare the glass with the clear glass. So that means the clear glass, if it is having, so by adding blind, by adding heat reflective glass. Okay, so by heat reflective blinds or with heat reflective films. Okay, so how much it is reduced? Okay, so it is going to be given by a coefficient called SC. Okay, so we are going to see that. Okay, so from that we are going to find out what will be the radiation will be entering through the glass. Okay, so that's point number one. Here in even in this also in wall also, so we are going to have a temperature. Okay, so you are going to have a temperature difference. So here the calculation is going to be based on UA delta T. Okay, so we have to calculate what is the overall heat transfer coefficient. Okay, so the overall heat transfer coefficient, it is U. Okay, or you can say it is a conduction coefficient. Okay, so you just take the resistance in the heat transfer. You might have studied the resistance. Okay, otherwise also the thing is very simple. Okay, it is resistance, conduction resistance. It is L by K. If it is one L1 by K1 for material 2, L2 by K2. Okay, so for building it's very simple. And if it is convection, it is 1 by Hi for inside. Okay, if it is outside, it is 1 by Ho. So that is going to be like this. So if all the resistance are connected in series, mostly in buildings these things will be in series only. Inside convection resistance, then plaster, then brick. Okay, then some then you're going to have plaster, maybe some insulation. So like that, then outside convection coefficient. So all will be in series mostly. Okay, and what we have to do if the resistance are in series, just you have to sum all the resistance. Okay, and you have to do the reciprocal of that. So that is called as U. Okay, overall heat transfer coefficient. So the heat transferred, it is given by UA delta T. Okay, so what is the delta T? So the delta T is given in the table. Okay, so is it connected with the radiation? No, it is not connected with the radiation, but it is connected with the so they have given. Okay, so they have given the values depending on the exposure, that is on the direction, and depending on the mass capacity. Okay, mass of the wall, kg per meter square area of the wall. So if the mass is less, okay, if the mass of the heat capacity is less, okay, so we'll be having a pattern. So if the heat capacity is more, okay, so for example, if it is concrete and other things, so the heat capacity is going to be very much higher. So that is what we have 4 variations. So highest heat capacity, so these two are medium, and lowest heat capacity. Okay, what is the significance of heat capacity? So this heat capacity, it is going to reduce the amplitude of temperature entering into the building. Okay, if I am having a higher heat capacity, so you will find that the amplitude will be very reduced to a larger extent. Okay, amplitude of heat entering, so it will be reduced to a larger extent. If the heat capacity is less, so it will directly, it will be like instantaneous. So directly it will be allowing the heat, okay, into the building. But all walls will be having some amount of heat capacity. So because of that, what it will do is it will shift the peak. That means if at 12 o'clock, if peak is there outside, okay, radiation peak is there at 12 o'clock. So the peak inside the room, when the peak will be there, it will be at 2 o'clock. Okay, or 2 o'clock for a building with lesser mass. Okay, Suppose if the mass is higher, it is 744. So what it will do? It will shift the peak to 4 o'clock or even 8 o'clock also. If the size of the building, okay, if it is more, and the capacity of the building, if it is more. So we have something called as lightweight construction, medium weight construction, and heavyweight construction. For heavyweight constructions, the shift will be very much higher, and the peak will be reduced. So that is the advantage. Okay, so that is the advantage. So we don't want the temperature to enter inside the building through the wall. So that means go for massive construction, or you reduce the size and you can increase the heat capacity of the material. Okay, so that we have to understand. Okay, so that is what is happening. So we have 4 varieties of material. Okay, so one is lightweight construction, the other is heavyweight construction, and okay, so this is the equivalent temperature difference for each direction it is given, and it is not connected with the radiation received at a place, but it is connected with the outside and inside. So that we are doing a correction based on the daily range. So you should know, very important. So daily range is connected with the radiation, because at the equator, you know that the temperature rise will be very much higher compared to other places. So we have seen the radiation map. So at the center, radiation within 23.5 north and 23.5 south, Tropic of Cancer and Tropic of Capricorn, the temperature, the temperature daily range, the rise in temperature will be very much higher. Okay, and that too in desert conditions and all, the daily range will be very much higher. Okay, so this wall temperature difference, it is connected with that daily range. Okay, so depending on the daily range, we are correcting this temperature difference. So how it is corrected? Okay, so it is corrected based on the TO max and TO minimum. This is daily range, and even outside temperature and inside temperature also. If inside is what? It is conditioned temperature, outside is the ambient temperature. So based on the ambient temperature and inside temperature, we have a correction. So that is there here, and we have a correction based on the daily range. So putting these two together, so you can do the correction for your place. For example, if I am coming to Chennai, so the daily range will be higher. Okay, so even the outside temperature will be higher, inside temperature will be lesser. Okay, so that means if I put all these things, so the temperature correction will be higher. But if I go to beyond 30° north latitude, so there you will find the daily range may not be that much higher. Okay, and the outside temperature, okay, so it will not be as high as Chennai. So there the correction will be smaller. So that means you are not directly through radiation you are controlling this. So you are controlling that through the daily ambient temperature variation and the daily diurnal variation. Okay, so just try to understand the concept. Okay, and so this is how. Okay, so this is how we are accounting for load calculation. Okay, so that means for all the directions. Okay, so for all the directions. Okay, we will be. I'm sorry. This is for all the directions we will be having the temperature difference. Okay, for from morning 8 to, okay, so 8, 9, 10, 11, 12. So and then I'm having 1, 2, 3, 4 up to 8. 8 to 8 I'm having. Okay, 8 to 8 p.m. So the temperature difference is because some transients will be there. Okay, so because for that only it is given, and you can see that. Okay, so okay. If it is a roof exposed, okay, so one case alone just we can see. Here you can see if the amount of if the capacity is higher, okay, so the peak has gone to the next day. Okay, so I think beyond 5 it has gone, and if it is lesser, okay, so what is happening? The peak has gone up to 5 p.m. Okay, up to 5 p.m. So the next 106 is going beyond 5 p.m. So 2 and 12 even further it is going. 3 and 19 still it is going. So that means what is happening? If the construction is massive, what is happening? It is shifting. The peak has gone outside the thing. So during night time the peak is appearing. Okay, so that is what you have to understand. So lightweight construction, so the peak shift will be less, maybe at 2 p.m. Okay, so the peak will be appearing. The temperature reduction also it will be less only. But if you are going very heavyweight construction, so that means the peak shift will go maybe at 8 o'clock at night, and the amplitude will be drastically reduced. Okay, so that is very important. If you go for simulation and all, you can actually you can see that. Okay, I will show that. Okay, so now we are going from wall to important components. So that is occupancy load. Okay, so what are all the occupancy load? So occupancy load, it is an internal load. So you may be knowing that occupancy load. I told if occupants are there in a place, so they will be releasing sensible as well as latent heat because of metabolism. And if they are seated at rest, the load added is smaller. If they are active, dancing, okay, and other working, doing heavy work, so the metabolic rate will be higher, so the heat added will be higher. And after that, it is dependent on the dry bulb temperature also. So if the dry bulb temperature is 20, so I'm finding 140, sensible heat is 140 and the latent heat is 125. Okay, but if the dry bulb temperature is 26, you can see that the sensible heat is 90 and the latent heat is 175. Why? Because you can see that when the temperature is lesser, the body releases heat sensibly. Because I told you in day 2, I told you that our body has a mechanism, control mechanism. So when temperature is lesser, it releases its heat through sensible route. Okay, latent is smaller. When the temperature is higher, okay, it is choosing latent route. Why? Because you know that latent route, it can dissipate large quantity of heat, because you are just evaporating water and releasing the moisture. So that means in that process you can release large amount of moisture. Just a small interesting thing that you can note. Okay, at high temperature, latent heat is more, sensibility is less. At low temperature, sensibility is more, latent heat is less. Okay, so this is for occupancy load. For whatever the condition, you can pick up these values and you can put it in sensible portion, latent portion. Okay, and the next is appliance load. Appliance load, whatever the capacity. Okay, depending on the capacity, so we will be having a sensible load and latent load. If it is cooking equipments, you will be having a latent loads also. Okay, so if it is motor, computer, all those things will be adding sensible heat only. And okay, so this is appliance load. So this will be inside the room. Okay, this is like a room load. And what is the significance of thermal properties? Okay, so properties, brick properties. I told the heat transferred into the room, it is UA del T. So how I have to calculate? U is calculated by L by K. So that means thermal conductivity is important. If thermal conductivity is very much lesser, that means that material will act as an insulator. So that principle we are using it for preventing the heat from entering into the building. Okay, in the summer air conditioning. Similarly, for avoiding the heat from moving from inside the building to outside in winter air conditioning. Okay, so that means we can select the material suitably for reducing the heat entry into the building and losing the heat loss from the building. Okay, so accordingly, so we have I have just shown a few materials for load calculation. But if you go to solver, okay, energy simulation solver, there is a very big material database is there. Just you have to pick the material and you have to put it. Okay, automatically it will do. Okay, material property is very important, not only for heat load calculation, it is very important for simulation also. Okay, so that is so we have a very big database. Okay, in all the building simulation software. Okay, even latest material like phase change materials also, it has been included. Okay, in the building simulation software. Okay, so what is the ventilation requirement? Already I told you. So as per Ishrae standard, okay, as per the ANSI Ishrae standards, for any person, I have to give some amount of thing. So that means if it's adult, engaged, and low level of activities, that means office work like that, 5 CFM per person is sufficient. If a person is heavily engaged, okay, so that means exercising, gym and other thing, dancing and all. So 20 CFM per person is advised, and are in another unit, SI unit, it is 10 liters per second per person. Okay, just you have to multiply. Okay, so that is how I told you. So if you are going up for a theater and all, so their ventilation is very important. If ventilation is not there, then it will spoil your health. So that is what I can say. Okay, so that means we have to take air from outside. Definitely we have to take air from outside. So that means if air is coming from outside, it is going to bring the load. Okay, so that we have to. Okay, so I will just go through a quick go through on the building survey. So today I'll just try to complete faster, because I'll take another 10 or 15 minutes. I will finish it, not like tomorrow, yesterday. So today I'll try to finish it faster. Okay, so whenever an engineer is going for any site, okay, so he will have the site drawing, and he will be taking a note. In that he will be noting what is the ground area, what is the height, what is the wall area. Okay, and what is the wall material. So all these things. What is the glass area? Okay, glass area. So and what is the direction also? It is important whether it is east, west, north, south, whether it is northeast, northwest, north. So that is also important. When you are doing load calculation, you will be having only 8 directions. You will have east, west, north, south, or southeast, southwest, like that you will be having. Okay, but if you are going for a building simulation software, their provision is there for you can give it in terms of degree orientation. So any direction you can take and it can calculate. Okay, so that is how you will be having. But in building simulation software, mostly we'll heat load calculation will be mostly using 8 directions. With that only we'll be doing. So that is what I call it as a direction. Okay, northeast, northwest, southeast, southwest, like that. Okay, and I have to note the wall area, direction, glass area, direction. Okay, and I have to know whether partition is there. So partition means outside you don't have the solar exposure, but it will be separating a conditioned space and unconditioned space. Okay, or both it can be conditioned also. Okay, so if both are conditioned, both will be maintained at the same temperature. Load may not be there. But if outside, if it is not conditioned, inside if it is conditioned, heat will be there. For example, inside your room you are maintaining at 25 degrees centigrade, but outside it is 35 degrees centigrade. Though it is not exposed to solar, but still from there, okay, from 35 degrees heat will be flowing through conduction. Okay, so that also I have to take into. So that is called partition. Okay, a partition, it can be a wall partition, it can be a glass partition, it can be a acrylic partition. So what all these things are possible. Okay, and this I think I have told you already. So how to calculate the overall heat transfer coefficient in a wall? Okay, so inside convection. So inside you will be having inside the conditioned space convection, plaster L by K. Okay, resistance, brick L by K resistance, then plaster L by K, then outside conduction. Outside convection, it is 1 by HO. So this is 1 by HI, this is 1 by HO. I have to add everything, I will get total resistance. Take reciprocal of that, so I will be getting the factor overall heat transfer coefficient. Just take U, multiply by the area, direction, area, okay, and temperature difference you have to take from the data, whatever I told. So if you multiply, you will be getting that load. Okay, and sometimes glass also will be contributing for this resistance, because glass you may be thinking solar radiation may directly enter, but if your glass is tinted, if it is fixed with the film, okay, so it will absorb some amount of solar radiation, so it will undergo conduction. Okay, so that is possible. And also one more thing also you can think. So suppose if you are going for winter air conditioning, so inside you will be hot, outside it will be cold. There may not be solar radiation from inside, which is hot, because you are maintaining heating. You are doing heating inside the room. So inside you will be maintaining at 25 degrees centigrade, but outside it will be at minus 10 degrees centigrade. But separating is glass. Now the process will not be radiation. The process will not be radiation. Okay. Now the process will be conduction only. Night time, no. So what will happen? So from inside, so I'll be having inside heat transfer coefficient, then glass, I have to find out L by K for the glass, then outside heat transfer coefficient, I have to sum it. Okay, so then I have to reduce that value. If you want to reduce the energy, okay, I have to reduce this value. Okay, some special type of glasses are there, so that we will, I think I have collected some data, so we can have an interesting discussion. Okay, so that we will have it subsequently. So then occupancy. Heat is added by the occupancy. Already we have discussed. Light. Just you have to note. You have to note. If an engineer is going, he has to note all these things. Then he has to do for heat load calculation form. And what is important? So dry bulb. What is outdoor dry bulb, wet bulb? So I told you from the data book you have to take it. Wet bulb temperature, RH. But these things cannot give meaning. But moisture content, specific humidity. So that will give meaning. Okay. Find out what is outdoor dry bulb temperature. Similarly, what is room design condition? Room design condition is 25. Outdoor, maybe for Chennai it is 37 degrees centigrade, okay, or 40 degrees centigrade. 40 inside I am maintaining at 24 degrees centigrade. So that difference. So this will constitute for sensible difference. So here outside the moisture will be higher, some grains per pound or grams per kg. So inside the grams per kg, it will be smaller. Outside the grams per kg is higher. So find the difference. You multiply that with latent heat. So that will be the latent component. So very simple. This will give you the latent component. This will give you the, this difference will give you the sensible component. Okay. So then we have to calculate how much will be the outside air through the apparatus for ventilation. So take the number of people, multiply as per ventilation standard, how much is the meter cube per person, multiply that, so I get the total volume. Similarly, you take the crack length through that 1 meter crack, how much your volume is, so multiply that, I able to find out. So you find out what is the total volume per minute. Very important. I given meter cube. You have to put it as meter cube per minute, because everything is based on rate only. What is the rate of heat entry into the room? Okay, so that is what I am trying to convince today. So next is the sun gain classes. So I told you. So the factors just now you have seen in the table. Take for each direction. It may not be east, west, north, south. You can use northeast, northwest, everything. That also, all the 4 directions you can put it. Okay, 8 directions you can put it. Area you can measure. Okay, and this coefficient, yes, is this coefficient. Okay, this solar coefficient. So this will tell you what will be the ratio of radiation transfer compared to white glass or a standard glass. I can say standard glass. If you have a standard glass, okay, if it is allowing 100%, so what is your glass is allowing? Okay, so that is given by this SC value. The SC value is lower, that means it will not allow the radiation into the room. Okay, so that is how. Okay, so we will be having, so we will be having SGC and SC. So all these things, factors we are going to discuss. We are going to have a separate discussion on class from energy conservation point of view. Okay, so at that point I will explain in detail. So now it is area into SC factor, and another thing is the watt per meter square. Just now what we have seen. Okay, for various latitudes. So I multiply, I will be getting what is the heat entry. Okay, sensible heat entry into the. Okay, and the solar and the transmission gains. Okay, so transmission gains, it is a wall. So wall, all the directions, even roof, even floor also I have to take it. Okay, so all the things I have to put the area, I have to temperature difference, I have to take it from that factor, U factor. Okay, overall heat transfer coefficient. So that is I have to put it. I multiply everything, I will be getting the total sensible heat through the walls. Okay, so here what is the total sensible heat through the glass, and I can find the transmission gains also. So except exposed wall and roof, what are the other things? Okay, so next room, partitions, ceiling which is not exposed to, and the floor. Okay, all these things. They are also what is the area, what is the temperature difference, what is the factor. Okay, U factor, multiply, you get the solar heat. Okay, sensible portion. Then infiltration and ventilation. Okay, the sensible component of infiltration and ventilation. So what is the infiltration quantity? Put the bypass factor. What is the density? What is the volume flow rate? What is the specific heat? What is the temperature difference? I told you MCP del T, but it is multiplied by bypass factor. Okay, and what is the heat gain? Watts? So that I am putting it here. Okay. Similarly, next is ventilation. For ventilation, I take what is the CMM, then bypass factor, density, and again the same things will be there. Okay, so I should not repeat. Same thing will be there. So except that this infiltration quantity will be going directly into the room. Ventilation, it will be coming from the through the outdoor air. Okay, so this is the sensible component of infiltration and ventilation. Okay, okay. So the next I have internal heat. So you know how many number of people, number of person. What is the sensible heat per person? Table just now we have seen. Just multiply. You get mostly it will be constant. And the motor, light, and other appliances mostly it will be constant. Except that cooking appliances where there will be some variation. Some computer, motor, fan, lightings, all these things will be having almost the same. Have the numbers multiplied by watt per number, you get the heat gain. Okay, so you add all these things. Okay, so this is internal sensible heat. Okay, and you add all these things, whatever you have seen so far, and this factor you will be having it in load calculation, but this you will not having it in the energy calculation. Okay, energy calculation you will be putting what is the actual value. Okay. Then we are going for room latent heat. So room latent heat because of outdoor air. So because of infiltration, ventilation, how the bypass factor, all this component. So here you can see this is humidity difference, not temperature difference. Humidity difference multiplied by latent heat, I get the what is the heat gain? Room latent heat gain because of outdoor air. Okay. So that also we are calculating. Then latent heat given by the moisture released per person. moisture released per people, or the directly sometimes heat will be given, you can add it. How much steam is released, that also you can add it. Okay, and after that you can add everything. Okay, this factor and all, it will be there for load calculation only. In energy simulation will not be there. So I'm then you can, if at all you want to have a design, you can calculate what is effective sensibility, effective latent heat, effective sensible heat factor, you can calculate. From that you can select the ADP, temperature of the coil. So from that you can calculate the dm by CM. All these things we have discussed already. Okay, so now okay, I think we have discussed this already. This slide is appearing again. Okay, I'm sorry. Okay, so now you know how to calculate the grand total heat. How you know how to calculate what is the CMO. Okay, so that also we know that. Okay, now we are coming to the most important conclusive point of this today's discussion. Okay, okay, so now I have calculated. Okay, so now I have calculated the load. Okay, I have calculated the load. So what is that I have calculated? I have calculated load calculation means I am taking what is the peak timing. So for that timing, I am doing the calculation. I am doing the summation of all the loads at that point. So I have done it. Okay, I have done it by simulation for a particular point. Okay, so I get some value. Okay, around 1100 something. I'm getting some value. Okay, so what is the meaning of that? In a load calculation, you are calculating the heat gain for a particular time of the day, for a particular peak time of the day. So what is that watts? So that is what you are calculating. So I have calculated. Okay, so I have calculated. Okay, so for that, what you are doing, you are going to the data book. Okay, you are going to the data book. You are trying to find out what is the ambient temperature at that point. So here you can see this is the time of the day, 24 hours. So since my peak is coming at that point, I am taking what is the corresponding ambient temperature. Similarly, what is the outdoor moisture at that point? What is the outdoor moisture at that point? I am trying to find out. And similarly, I am trying to find out what will be the solar radiation. So here you can see at the east, this is morning, I am having radiation. West, I am having a radiation at the afternoon. Okay, so then you are having the wall north. Okay, in the north I am having, because I am calculating for July. Chennai at July only we will be having north exposure. Okay, so we are having a north. So here you can see for south, it is 0. You can see that it is 0. Okay, so that means okay, this is okay. So what is this? These are all the radiation calculations from outside. Okay, from outside. But when you are going for a load calculation, what you are taking, you are just taking what is the ambient temperature. That is ambient temperature. You are going to the data book and you are trying to find out what is the ambient temperature, peak ambient temperature for Chennai. Okay, and you are trying to find out what is the corresponding specific humidity. Just now you have seen. Similarly, we are trying to find out what is that radiation value at that point. Similarly, we are finding what is that radiation at maybe this is a roof radiation, it is higher. Next, I am having a west radiation, it is higher. So these values only we are going to calculate. We are not going to calculate east values on that. Why? Because we are very much interested in calculating what is the peak time of the peak day, peak time of the peak day. So we are just making one calculation. So what is that you are calculating? You are calculating the tonnage. Okay, what is tonnage? It is kilowatt. Okay, it is kilowatt. So kilowatt means it is kilojoules per second. Okay, so that means you are trying to calculate. Okay, so we have calculated. Okay, what is the load entering? So these are all the what are the data we are taking. Okay, what are the input data we are taking? Inside, what is happening? Inside, what is happening? So inside we are having, okay, so roof I'm having. So you can see roof is not a maximum at 12 o'clock. Okay, roof, but actual as per radiation it should be at 12 o'clock. But we are signing that roof is not maximum at 12 o'clock. It is getting shifted because of that. I told the transients, it is getting shifted. And you can see all the other things are also it is getting shifted. Okay, so this is east and all the other things. When it is passing through the wall, okay, the amplitude is getting diminished, but it is not for roof. Okay, nothing to worry, because my roof is not insulated. It is not insulated, it is not treated. So that is why it is like this only. No problem. So I am getting the maximum value here. So that point I am taking it as a maximum. So similarly, I am trying to calculate what is the load corresponding to that. Inside the room, I taken three people are there. For that, I am getting what is the latent load. Okay, so this is a sensible load. I mean, this is latent load. This is a sensible load in watts. So both I'm adding. So this is the overall load what I'm getting. So what is the load you have calculated? So I have calculated a load of around 1120 watts per second. So it is less than half tens. Okay, it's a small room. I have taken just a small experimental room. For that, I have done the load calculation. So if I am doing the load calculation like this, so what is happening? So I am trying to calculate the rate of heat gain into the room. So that is 1120 watts per second. So if you are doing the load calculation, okay, if you are doing a load calculation or tonnage calculation, there also you are doing the same thing only. You are calculating but you are calculating only for particular point of time. If I want to do the same thing for energy simulation, okay, now I am an energy simulation engineer. So what I should do, instead of calculating for one point, I have to calculate for full day. Okay, so that is very important. So if you want to calculate for full day, so what are the data which is required? I require data for all the 24 hours. So ambient temperature I require for all the 24 hours. Okay. Similarly, what is the outside specific humidity variation for all the 24 hours I require? Similarly, the radiation between morning and evening, morning 6 o'clock to evening 6 o'clock, what is the radiation? So that means these are all the input that I have to give to my energy simulation model. Okay. And then I am giving to the energy simulation model what is happening inside. So I have given a set temperature of 25 degrees inside the room. So how much amount of heat is entering the room? Okay, through the roof. So this is the output. These are all the output through the roof. So this is the heat entry. So through the east. So there you can see it is the values are higher. After entering through the wall, the east entry is smaller, the west entry is smaller. Something is getting shifted also. That is getting shifted. Okay, even the south, the peak was here. Now you can see the peak has gone to night time. Okay, so that means each wall is having its own characteristics. So that means if you do an energy simulation, you will get a better picture what is happening inside the room. And also, if I am including the latent load, the corresponding that also, so I can calculate even latent load also for 24 hours. Okay, I can calculate the sensible load for 24 hours. I can calculate the latent load for 24 hours. Okay, so because of that, I am getting the overall energy for 24 hours. Okay, so what is the difference between the load calculation and energy simulation? Load calculation you are doing for particular 1 hour, peak day, peak time. What is energy simulation? With you are taking the full data for which the simulation is required. You are taking the input data. You are doing the calculation for 24 hours. Okay. Why 24 hours? It can be 1 month also. You can do it for 1 month if data is given, because you have seen the solar data. It is there for throughout the year. So why 1 month? You can do it for 1 year also. Okay. So that is how you can calculate these values. Okay. For 24 hours, you can calculate it for 1 month. You can calculate it for 365 days. Okay. So that means I have done the energy simulation. Okay. So that is how the load calculation and the energy simulation is linked. Okay. So now you can ask, see this all this place what it is giving, it is the rate of heat entry into the building only. Okay. How I can convert that into energy? Okay. How I can convert that into energy? So the rate of heat gain into the building, it is 1120 watts, that is joules per second. Now if I want to calculate for 1 hour, okay, so then it will become rate of heat gain per hour, it will become, so 1120 into 60 joules per minute. I'm converting seconds into joules per minute. Similarly, if it is per hour, I have to multiply 60 into 60. So energy consumed per day, so you take the values at each hour and multiply by 3600. How I can do that? So this is the value consumed at each hour. So that means you do the load calculation for each hour, like how you have done for the peak timing. So that is joules per second. So you do the calculation for each hour, one calculation. Okay. And you just try to average for 1 hour. So how you can do that? For each hour, you find what is the wattage, multiply by 3600 for 1 hour. So that means I'll be getting the energy. So this will be like this. So you think that for hour 1, so I have the value, just multiply by 3600. So this is hour. So second hour, value 3600. So value 3600, value 3600, value 3600. The original graph is like this. Okay, since I am averaging for each hour, my values will be like steps like this. Okay, that means there is a accuracy problem is there. Accuracy problem is there. If you, for example, you take, I can do the same calculation even for 2 hours also. So okay, so even I can do it for 2 hours also. If I do for 2 hours, so I take one value from each of 2 hours, then I have to multiply by 2 hours. So that means instead of 3600 seconds, I have to multiply by 7200 seconds. So that means first value, I cannot do that for first value because half only will be there. Second value will be into 7200, next value 7200, next value. So like that, I'll be having big blocks here. So that means still this will not be accurate. If I am doing for 2 hours, it will not be accurate. So what you have to do, if you want to improve the accuracy, you can reduce this step of calculation. So even you can calculate it for 1 second also. So I have done this simulation, okay, for 1 second only. For every 1 second I have done the calculation. So you can see I am getting a very smooth curve, and I can very confidently say that this is very accurate. Okay, I can very confidently, because I'm calculating for every second. I'm calculating radiation for every second, humidity for every second, and all the calculations I'm doing it for every second. So that means just if I multiply all the values, if I add all the values, I'm going to get what is the total energy. So what is the energy? What is the difference between the rate of heat entry and energy? You multiply the rate of heat entry into time, that will become energy. So for example, if I'm multiplying 1120, it is joules per second. If I multiply by 60 seconds, then it will become so many joules per minute. Okay, so many joules per minute. So if I multiply by 3600, then it will become so many joules per hour. Okay, and if I am doing it for every hour, okay, if I am doing it for every hour, so I am taking all the values like this. I am taking all the values. I multiply by 3600. Okay, multiplying everything by 3600. I am calculating that value. So this is the heat entry into the building. So what will be the energy consumption? For example, if you are using a air conditioner, so this will be the heat entry. So the amount energy consumed will be, I have to divide it by COP. What is COP? Cooling effect by heat energy output. So cooling effect will match with this. This much amount of heat you have to remove that. Okay, so that means this heat, okay, this much kilowatt. Okay, so this amount of heat just divide by COP. I am assuming a COP of 3. So that means I am trying to find out what is the value. So the value is 5.69 kilowatt hour. So that means this is the electrical units that it will be shown by this. So the unit of this after multiplying by time, so this becomes joules, this becomes kilojoules, this becomes kilowatt hour. So this is energy. So that means rate of consumption multiplied by time, only it will become energy. Okay, rate of consumption is like kilowatt. So even the load what we are calculating, it is in kilowatt only. It is in kilowatt. That is very important. You should understand whether it is cooling load or heating load. We are calculating it in a kilowatt only. Okay, and when we are multiplying by time, then becomes energy. So what is that you are doing? Mathematically, we are doing the integration. Okay, so we are doing the integration. So it is numerical integration. You know, in numerical integration, if the step size is very smaller, so what will happen? Accuracy will improve. So for example, if comparing to this, if you do this, the accuracy will improve. Comparing with this, if you have it like this, the accuracy will be very much higher. So actually, I have done for you every second. So that means this calculation will be perfect. That you have to understand. Okay. So that is what I wanted to tell you today. And this is what I have calculated for 2 hours. And I have calculated the electrical energy. This value will be different from that of what I did for 1 hour interval basis. 1 hour interval basis, the value is smaller. For 2 hour interval basis, okay, so almost okay, 2 hour interval basis, the accuracy is not good. Okay, so the value is increased. Okay, here you can see the value is increased. Okay, so that means it is not accurate. Okay, so that means if you are doing numerical integration, so the step size you should always reduce. If you reduce the step size, you will get a very smooth curve. Your calculation will be very smooth. Okay, so for that purpose only, I have done calculation for every second. Okay, I have calculated what is the values. Okay, So that means what? For every second I have to calculate the value, multiply by 1 second. 1 second means what? That is the actual value. Just I have to add the values. I will be getting what is the total energy consumption. Okay. So now I conclude. Okay. So heat load calculation and energy calculation. Okay. So heat load calculation is what we calculated for a particular point of time. Okay. Energy calculation, it is the calculation for time interval. It can be for 1 day, it can be for 1 month, or it can be for maximum 1 year. Okay. And you calculate the energy, you multiply it by the time duration. You calculate the rate of heat flow or rate of heat entry or rate of heat gain, multiply by the time. So you will be getting the energy. Okay. So that is how we will be doing the energy simulation. That is how the data we will be receiving in the energy simulation. Okay. Thank you. I think today also I have gone extra time. I think some important informations were there. So that is why I have taken extra time. Thank you for joining. So if any doubt is there, you can post your doubts in the chat box. I'm just seeing the chat box. Okay. You can post your questions now. All of you, are you listening? Are you listening?
Yes, sir.
Yes, sir.
Yeah. Okay. If any doubt is there, you can just post it here. Okay. Any doubt is there? No doubt is there? Why? Have you understood? Just put, if you have understood, just put, we have understood in the chat box. Or you have understood very well. Like that you can put. Don't put like that. Whether you have understood or not understood, just put that in the chat box. Because I'm wondering, I should not be in a different, I should communicate with you. So I should not be somewhere in a different place. Okay. Whether I am able to convey my message very clearly. Yes. No message is there. Christina, clear, understood. Okay. No, Mr. Shah, see, 0 south or 0 it is same only. Okay. It represents a single line only, equator only. Okay. No, we don't have different data. Same data only we have. Okay. Same data only will be. Yeah. We don't. Please refer to the data. We will not have different data. We'll be having a different data only, but the peak will be different. That you should know. The month that week, because when the sun is traveling from Capricorn to Cancer, twice in a year, twice it will be crossing the equator. So that means twice you will be having the peak. That is during equinox. That means March 22, okay, and September 22. Twice it will be crossing. So that's why 2 peaks will be there. Okay, during March and September, 2 peaks will be there. But equator is at 0 degree only. Okay. Yeah. Is that Mr. Shah? Have I clarified your doubt? What measures can be taken to reduce heat load? See, insulation, coating. Okay, and glass means you can go for film tinted glass. Okay, heat reflective glass, single pan, double pan, multi pan glasses. So all these things we are going to discuss. You need not worry. So we have so many days. We are going to discuss all these things. Okay, so don't worry. Yeah. I think Mr. Shah, you can unmute yourself and you can talk, because if whatever I told, if it's not clear, okay, you can unmute yourself and you can talk. Okay, thank you. So yeah, all heat on the outer surface is going to enter the room irrespective of the specific heat of the material. All the heat on the outer surface, no, it will not enter. Okay, if you take the glass, in the glass, the heat will be entering. So if reflectivity is there, some portion will go outside. Similarly, even if heat is absorbed, in the glass. So it will compare inside the room temperature. If it is a conditioned room, inside the room temperature will be lesser. Outside the room temperature will be higher. So that means where the temperature is lesser, there the heat flow will be more. Similarly, if it is an unconditioned room, okay, when the heat is entering, sometimes it is possible inside the room the temperature may be higher. Outside the temperature may be lower, or some wind velocity will be there. So always in the glass, when if absorptivity is more, the glass will absorb the heat and it will be having, and it will be just seeing where the temperature is lower and where the convection coefficient is where the convection coefficient is correct or where the resistance by convection coefficient it is lesser. So it will heat will try to move that way. Okay. So two things it will see, whether the temperature difference as well as convection coefficient. Okay, so wherever it is lesser, it will go to that place. Okay, so it will always, it need not that heat will and it should enter the building. Okay, so if it is coming to the glass, it can enter into the building, even it can go out of the building also. If outside temperature is lower, similarly if outside convection coefficient is higher, heat can go outside the building also. That is possible. Okay. How to take care of variation in load while designing the system? Do energy simulation, because if you are doing it for 24 hours, what are all the variations that is happening for a day that you can understand. Similarly, if you are doing it for a month, even monthly variations also you can understand, because you think for Chennai, so December it will be cooler and June it will be warmer. So if you do the energy simulation, monthly variations in the energy consumption also you can understand. So daily variations, monthly variations, you can find out if you are doing simulation. So based on that, if you are doing the design, so that will be the best possible design. Okay. For brick wall, for example. So even in a brick wall also, see in brick wall some interesting cases are there. So think that during daytime it will be absorbing the heat, okay, and it will be storing. So think that the heat capacity of the brick is higher, so it will absorb the heat. For example, at 4 o'clock it will be having maximum 4-5 o'clock it will be maximum amount of heat. Once the night comes, okay, during night times, what will happen? Maybe at 5 o'clock, 6 o'clock, 7 o'clock, 8 o'clock, inside the room it will be very hotter, but outside the room, because of wind flow, sea breeze, okay, it will be colder. So you will be always thinking that it will be entering into the building. No, since inside the room, because of load or because of some thing, so the temperature will be higher, but outside the temperature will be lower and the wind flow also may be there. So what will happen? From the wall, heat will flow towards the outdoor. That means outside the building the heat may flow. Okay, so it all depends. Okay, it all depends. Okay, heat will enter into the wall. It will just see which side the resistance is lower. So that side the heat will flow. So heat will always flow in the direction of decreasing resistance. Okay. Yeah, so I think that also we can discuss in detail. Maybe subsequently on one day. One day I will dedicate for discussing about glass, energy conservation in glass. Similarly, I will we can discuss about wall also. Okay, so energy conservation wall also we can do. Okay, yeah. See, any other question is there? Yeah. So if there is no other query, okay. Okay, in most cases, brick is not directly exposed. Does plastering and painting HPM make? Yeah, definitely it will make an impact. So if it is if your paint is heat reflective paint, or if it is reflecting the radiation, so that will have the effect. Even plastering also. So if the plastering means if you are plastering with less thermal conductivity material, so that will also have its effect. Okay, that will also have its effect. Similarly, you can do insulation also, overdeck insulation, you can do it. So that also it will have its effect. Okay. So whatever it is possible from thermal point of view, so whatever it possible, you can add insulator, you can add heat reflective paints. Okay, so you can add surface. Okay, if your surface is not smooth, okay, then also there will be a reduction. You know that. So because if the surface is smooth, radiation will enter very easily. If there are some perforations at the surface, okay, so then the radiation cannot enter into the building. So so many methods are there. Okay, so many methods are there for reducing the heat entry into the building. Okay, yes. Okay, I think there is no other questions. Okay, sir, any question is there from YouTube streaming?
No
Thank you.
questions, sir.
No questions. Okay, so if there is no question, thank you. So we will meet on Monday. Okay, so next week we will discuss about energy simulation. Okay, in detail. Okay, in detail about the energy simulation. Okay, what is the background for energy simulation? Few case studies also we will discuss. Okay, thank you.
Okay, thank you, sir.
Yeah, thank you.